Alright, subscribers, welcome back to another episode of Science with Surback. Today what we're going to be looking at is reaction classification in section 10.2. Now the objectives for this section is to 1. Classify chemical reactions, and 2. Identify the characteristics of different classes of chemical reactions. So we have many different reactions, and there are several thousand, several millions of reactions that we have to worry about here. And what we do is we categorize them to help us focus or to help us identify these chemical reactions. And really what that does is it helps predict our products. So what we'll do here is we'll take a look at each of our 5 different types of reactions that we're going to use in this class. And so I'm not going to get into too much detail here because we will identify each of these reactions. So we start out here with a synthesis reaction. And what we have here is the general formula. Again, these are not any substances or not any atoms or molecules. They're just generic formulas. And so it's when 2 or more substances produce a single product. So what we have here is some examples where we can see, hey, we can have 2 individual elements make 1 compound, or we could have 2 compounds make a single product compound. Okay, so we move on here to a combustion reaction. And I clump these things together because sometimes here with the combustion reaction, it's very, very similar. It's not the same, and we'll see why here in a second, but it's when oxygen combines with another substance to release energy. Now, both of these things here in our examples have oxygen, and they produce one particular product. However, we can get a little bit more in depth and in detail, and that's when we have a combustion reaction that is going to produce water and hydrogen. So when you have a hydrocarbon, hydrogen and carbon compound, like methane or CH4, combined with oxygen, always, it's going to produce CO2 and H2O. Again, that's very important here, is that when you have a hydrocarbon react with oxygen, you're going to produce CO2 and H2O. Only with a hydrocarbon. Now this says it's not a synthesis reaction because we have 2 products on that right hand side. Alright, so let's go ahead, let's try some examples here with synthesis and our combustion reactions. So we have sodium and oxygen. This right here is a synthesis reaction, and it's going to combine sodium, Na, and oxygen. So sodium and oxygen, remember, would be ionic. So Na would be a 1+, O would be a 2-. So what they would form is Na2O. Now, one thing that we have to do from here on out is balance our chemical equations. So we look at our Nas. We have 1 on our left, 2 on our right. The way in which we do this, or the way in which we balance this, is we're going to put a 2 right over here. Now we get to oxygen. We have 2 on our left, 1 on our right. So we put a 2. Now what that's done is that's increased our sodiums to 4. So we need to make this a 4. And this is why I always say balance with a pencil. So we have 4 Na, and now this particular equation is balanced. All right, so now we have our benzene, C6H6, and our oxygen. We have here a hydrocarbon. This is a hydrocarbon here on the left, and an oxygen. And so what happens here is this. When you see a hydrocarbon and oxygen, 2 products, it's going to produce CO2 and H2O. So now we get underway and we start to balance. Over here on the left, we have 6 carbons. On the right, we have 1. So we make that a 6. We have 6 hydrogens on the left. We only have 2 on our right, so we need to put a 3 out in front to get us to 6. And then what we do is our oxygens. We have 2 on our left, and now be careful. We have 6 times 2, which is 12, plus 3, 15. We want a whole number out in front here. So we've run into this dilemma before. We pretend oxygen doesn't exist, and we double every coefficient that we have. So now, the only thing that we should have to balance is our oxygen. So we have 12 times 2, which is 24, plus 6 times 1. That's a total of 30. 15 times 2 gets us 30. So that's how we would balance our particular reaction here. Now we have our words equations, all right? So we have solid aluminum and sulfur react to produce aluminum sulfide. So we start out here with aluminum. Now, because it listed the state of matter, let's go ahead and list the state of matter in parentheses. So that's an S for solid. Now, sulfur is the element S. Now, it said it was also a solid, and so it's going to react to produce aluminum sulfide. This is an ionic compound, so aluminum sulfide, remember, is Al3+, S has a 2- charge, so when they produce aluminum sulfide, it is Al2, S3, and that is also a solid. Okay, so over here on the left, we have 1 aluminum. On the right, we have 2, so we need to put a 2 coefficient out in front of Al. Our S, we have 1 S, and we have 3 S's, so we put a 3 out in front. And this is how we would balance this particular reaction. Now, our fourth problem here says water and dinitrogen pentoxide gas react to produce aqueous hydrogen nitrate. Okay, so we start out here with H2O as a liquid, L for liquid, plus dinitrogen pentoxide. Dinitrogen pentoxide means we have 2 N's and 5 oxygens. N2O5, and the problem said it's a G4 gas. This produces hydrogen nitrate. So remember, hydrogen would have a 1+ charge, nitrate would have a 1- charge, and when we would form that particular product, it would be HNO3, and it's AQ to represent that we have aqueous, okay? So now, we get into this. We need to balance this. We have 2 H's on the left. We only have 1 on the right, so we put a 2 coefficient out in front. And then we have, be careful, oxygens. We have 1 plus 5, so total is 6. 2 times 3, that is 6. And then we have 2 nitrogens. 2 times 1 is 2 nitrogens. So that problem right there is balanced. All right, so let's keep moving on here to our different type of reactions. So a decomposition reaction is when you have a single compound or a single reactant break into many parts, at least 2 or more elements. It's almost the opposite of our synthesis reactions. Again, this is just breaking down or decomposing into simpler parts. So let's go through, let's write some examples. We have aluminum oxide, which it's an ionic compound. It forms Al2O3, and it says it is decomposing when electricity is passed through it. Okay, so what that means is we're going to split apart these elements. Okay, so what we have here is this, Al. Now, you check, always check if you have a single element, is it diatomic? Meaning we need 2 of those elements when it's written by itself. Well, Al is not diatomic, so we can leave it as that. And then we have oxygen. We have O, but it is one of those 7 that are diatomic, so we have O2. Okay, so now we need to balance this. Al2, which means we need 2 Als, and then we have 3 oxygens. Well, 3 and 2. Remember our rule of thumb about 3 and 2? They meet at 6. And so we need a 3 here. We need a 2 out in front. And then that would increase our aluminums to 4. Okay. Now, nickel 2 hydroxide. I'm going to go quick on this one. We would have NiOH2 decomposes to produce nickel 2 oxide and water. So nickel 2 oxide would be NiO plus our water H2O. Okay? So Ni is 1 on the left, 1 on the right. Our oxygens is 2 on the left, and be careful here, it's 2 on the right, and then our H's is 2. Well, that right there is already balanced, so that works out pretty nice for us. All right, so now we have hydrogen carbonate, produces sodium carbonate and carbon dioxide and water, okay? So hydrogen carbonate here, remember, would be H2CO3, is going to produce, sodium hydrogen carbonate. I messed that up here. Sodium hydrogen carbonate would be NaHCO3. Okay, so NaHCO3 starts us out with our reaction, and it would produce sodium carbonate, so Na2CO3, carbon dioxide, CO2, and water, H2O. Okay, so we go to balance. We have 1 Na on the left, 2 on the right. We produce 2. Okay, now we have 2 H's on the left and right, so they're good. We have 2 carbons, and be careful here. We have carbon 1, carbon 2, so we're good. And we have 6 oxygens. We have 3 plus 2, 5, plus another 1, which is 6. So that right there is balanced by just putting that 2 out in front. All right, so moving on here, these are really important reactions. We see them quite a bit. We have our replacement reactions, which we categorize into 2 different categories. Single replacements, what we'll talk about now, and then we'll move to double replacements. So a single replacement reaction takes one single element and bumps another out of the compound. And you can see that it has this particular general formula. Now, what we have to be worried about here with our single replacement reactions is our chemical reactivity, okay? So I know this is blurry right here, but what happens here is that when we talk about a metal must be more active than the metal in the compound to be able to produce our products, okay? So a single element has to be higher in this list than a element or a metal in the compound. If it's not higher, then the reaction does not happen, and we simply write NR for no reaction. So let's keep those things in mind, the general formula and this chemical reactivity, as we go through this particular process. So again, just to emphasize this, a metal that is by itself has to be above the other metal in the compound to bump it out or replace it. It has to be, by definition, more active. So keep this list handy as we go through the next particular examples. All right, so what happens here is this. We need to figure out, okay, how can we use this list to predict our products? So we start out here with this. We need to figure out what replaces what. Well, magnesium is a metal, so it's going to try to bump out, I'm going to draw an arrow here, aluminum, okay? So what we need to do is we need to go to magnesium, and we need to find it. And magnesium is right here. And we need to see, okay, is it above aluminum? Well, yes, it's above aluminum. So therefore, we can write this particular reaction. So it's going to produce magnesium chloride, which is MgCl2. And it's going to bump aluminum by itself. Now, aluminum, always double check to see if it's one of the diatomic. It is not, so we can just write Al. Okay? Now, don't forget to balance this particular reaction. So we have MgCl2 and Al. So Mg and Mg, they're both 1 apiece. Al and Al, they're both 1 apiece. However, Cl is 3 and 2. Remember, our 3-2 combo meet at 6. So we'll put a 2 out in front of here, a 3 in front of the Mg. So this means we need 2 Al and we need 3 magnesiums. So now we are balanced. All right, so now we go down to this final equation here. Bromine is going to try to react with magnesium chlorate. Now, bromine is a halogen, so it's not going to try to bump out the metal, it's going to try to bump out the non-metal. So we go and we say, we find bromine, it needs to be above chlorine. Well, it's not, it's below chlorine in this list, so we simply write NR for no reaction. And that is how we would go through this particular types of reaction. Again, you have to find out what replaces what and then figure out, is that single element higher in the list than that element in the compound. All right, moving on here. Double replacement reactions. All right, so now double replacement, we are going to have partners switch, right? Think of this as a square dancing, right? You have partners switch, or ions exchange is the technical chemical term. So how we do this is we have to split apart our particular elements that are involved. And I'm going to start here with problem 3 and work our way up to problem 1. So again, we need to split our ions. So what I'm going to do here, just to help us out, is I'm going to split our particular ions. So this right here, we're going to have potassium react with chlorine. Well, potassium is K+, and our Cl is 1-. So what we're going to have happen here is this. Potassium and chlorine are going to combine together to form potassium chloride, and barium and carbonate are going to form barium carbonate. Okay, so you would form BaCO3. Now, we still have to balance our reaction here, so we would have to put a 2 in front of our KCl. We would have to then check and see we have 1 CO3, we have 1 CO3, 1 barium, and then 2 chlorides. So that is balanced. All right, so on this one here, the next problem here, again, we're going to split the difference here of our ions. So this time calcium and phosphate would combine together, and they would form Ca3PO4 and H and OH. Now, H, remember, I'm going to write this out to the side as H1 plus OH1 minus. You could write it as HOH, but whenever you see this, it is going to be H2O. It's going to be water. And so what we would do here is this. We have to balance it, so we'd need 3 out in front of calcium. We would need our next element here to be our oxygens, which I'm not going to count PO4, so don't count PO4. So I have 3 times 2, which is 6 oxygens. I only have 1 oxygen over here, so I just need 6. And then we go to our hydrogens. We have 3 times 2, which is 6, plus 3, that is 9 hydrogens. Okay, so now we're going to have to work a little bit here. But before we go there, remember, we need 2 PO4s. So what we're going to do is put 2 PO4s, and hey, looky there. That balances out our particular equation. All right, so let's do this. Since I'm running out of room, let's move problem number 1 down here. Okay, so it says aqueous lithium iodine, which, again, think back to your naming protocol. Lithium iodine would be LiI. Reacts with silver nitrate. So silver would be AgNO3 2. To produce solid silver iodide, so AgI, and aqueous lithium nitrate, which would be LiNO3. Okay, so now it told us the products here. That makes life a little bit easier, and all we need to do is balance. Li is 1 on the left, 1 on the right, we're good. I is 1 on the left, 1 on the right, we're good. Silver is 1 and 1, we're good. However, our NO3 2 needs to be balanced. And let me double check. That is a mistake. It should be Ag1 plus and NO3 1 minus. That is a mistake on my part. It should have been written as AgNO3. Again, silver nitrate should be written as AgNO3. And right now, this is balanced. Again, I made a mistake writing that. It should be AgNO3. So right now, this problem here is already balanced. All right, so our final thing here, which if we had some more time, we would talk about, but is what happens when we put two liquids together and they produce a precipitate. And so we have to remember this, that in a double replacement reaction, we're going to get three results. We're either going to get two liquids that mix together to form a water, a precipitate, which we can say is a solid, or a gas. And so what is shown in here, this wispy solid here, is what we would define as a precipitate. All right, so we'll get some more practice balancing our chemical equations. I hope you have enjoyed this episode, and as always, make sure you subscribe.